All right. So our final class of compounds to consider for aromaticity are commonly referred to as PAHs. You may hear that term in some popular media and other places. This is polycyclic aromatic hydrocarbons. Polycyclic aromatic hydrocarbons. So benzene, and we can then fuse another ring onto it. This is naphthalene. We can even add another one. And this is anthracene. Anthracene. So, are these compounds aromatic? Well, of course, they violate rule number 2. They're not strictly monocyclic. But I've drawn these with a deliberate double bond pattern to make this easy for you. Imagine if those fused bonds here didn't exist. Then you can see that we have this outer ring that would look like a monocyclic ring. So if we can find that resonance form, then we can see that these are also aromatic compounds that otherwise strictly fit our rules. So we have 2, 4, 6, 8, 10 high electrons. That's one of our Huckel numbers, remember. Let me go over here. So if n equals 0, this was 2, 6, 10, 14, and so forth. Go ahead and put 18. So with 10 pi electrons, we see that naphthalene fits our criteria for aromaticity. The same thing with anthracene. It's fully conjugated. It's planar. Everything is sp2 hybridized. We have this outer ring that we can look at and consider kind of like our monocyclic if those double bond or fused bonds in the middle here didn't exist. And so we see that anthracene is also aromatic. Now, one of the nice things is that then all of these ideas can go together. We can have polycyclic and aromatic compounds. This one, for those of you from biology class, you know that that's purine. Again, the pyrimidines and the purines that are important nucleobases. So all of this is going to be building up to your understanding later in this semester of biological molecules, DNA, RNA, chromosomes, carbohydrates eventually, and other things that are very important for biology. So we have a wide variety of molecules that we can have aromaticity present in that molecule, and that governs the reactivity pattern. So these double bonds, even though in our valence bond theory, that is this localized bond picture, we have this as a double bond, it's not really like an isolated double bond. And that's the lesson that we take away from all that we've learned about benzene, is that those are not simple alkenes, that when we see those 3, or in this case 6 pi electrons or higher numbers, they react differently. And so, for instance, if we subjected naphthalene to Br2 plus FeBr3, because we see it as an aromatic compound, then we predict that the product is not an addition product, but a substitution product like we saw with benzene when we started our discussion in the chapter.